This is the New England Journal of Medicine COVID-19 update for February 23rd, 2022. I'm Stephen Morrissey, managing editor of the journal, and I'm talking with Eric Rubin, editor-in-chief, and Lindsey Baden, deputy editor. Eric and Lindsey, we've grown accustomed to respiratory infections that occur in waves. For many infections, these waves occur seasonally. The best example is influenza, which spreads around the world each year and reaches North America in the late fall and winter. But COVID-19 has been somewhat different. There have been waves of infection, but they've occurred largely coincident with the appearance of new viral variants. Some of those variants have been very successful, such as Delta, which appeared almost everywhere and caused a good deal of highly morbid disease. Others, such as Beta, have been more geographically restricted. But from the standpoint of spread, the winner has been Omicron, the cause of the most recent wave. Omicron spread widely, even among communities with high levels of pre-existing immunity. So let's talk today about a study we published about Omicron and get some perspective on what it might mean for the future of COVID-19. Before we start with the study, though, Lindsey, can you help us understand the virology? What's different about Omicron and how might that affect the biology?
So, Steve, it's very hard to discern mutations and their biologic implications until we see how it behaves clinically. However, what we do know about Omicron from being able to sequence it, we understand that it has at least 30 mutations, half of which are in the RBD, the receptor binding domain, some insertions and deletions as well. What we know from prior variants is that some of these mutations can alter the binding affinity, so how well the virus binds to cells. Some of these mutations likely affect transmissibility. Others have immune evasion properties. This has implications on how well the virus can spread, on diagnostics, as we understand which diagnostics detect which sequences, therefore may be altered by genetic changes. For example, S gene target failure, which is a deletion associated with a target that some diagnostics utilize, allowing detection of certain variants. It also has implications to immune responses in vaccines and therapeutics, with alterations in the virus's exterior wall or its outer protein spike, thus averting some vaccine-elicited immune responses, as well as some of the targets of monoclonal antibodies. Less likely at this time that it has implications for small molecules like some of our oral antiviral agents. However, ultimately, the implications of the mutations will best be understood through clinical study and seeing the actual biology in the community.
Lindsey, something unusual about Omicron is it helps us understand a little bit about the family tree of the SARS-CoV-2 variants. And that is, it's not really a linear form of evolution. Omicron has many changes. Some of those are shared with other variants, but many of them aren't. And there isn't a progression from one variant to another in an easily predictable fashion. So what that means for the next variant is it could look like Omicron, but it also could be very, very different from Omicron. Certainly, this virus has shown that it has the ability to explore a lot of genetic space. And that raises the question of how effective previous infection and vaccination will be in the future. I don't want to be alarmist about it at all. In fact, I suspect that we will be getting some degree of protection against these new viral variants, but they could be very different.
So, Eric, I think you're getting at the issue of evolutionary pressure and whether SARS-CoV-2 is responding to, let's say, population immunity, perhaps as elicited by prior infection or vaccination. Therefore, the new variant has to overcome that barrier. Whether there is chronic infection, perhaps in individuals with a weakened immune system, allowing the virus through time to develop enhanced features that allow it to more favorably transmit and infect, or whether there's an interaction with zoonotic reservoirs that allow other gene swapping and evolutionary events, as we see with influenza, when we talk about influenza's shift and drift by analogy. So you're absolutely right that the next variant may be a more simpler modification of a predominant variant, or perhaps a more significant shift depending upon the evolutionary opportunity of the virus gaining features that allow favorable transmissibility in the background of community immunity. Because that is a feature that we are studying currently and trying to understand. How does the virus be successful when large numbers of the global population have some degree of prior immunity of a different form that it has to overcome, be it vaccine or natural infection with a variant of different sorts?
It's clear that the biologic differences in the Omicron variant have led to an altered epidemiology. So looking at the study we published today, it comes from South Africa, looks at the Omicron wave in that country. What did we learn from this study?
Steve, the study was performed in Gauteng province, an area of the country that includes Johannesburg. The Omicron variant was first identified in Gauteng in late November of 2021. This report consists of two parts: a serologic survey and a description of the epidemiology of acute disease. Thus, it provides a look backward at pre-existing immunity and a look forward at infection through the middle of January. The participants in the serologic portions of the study had been sampled systematically starting in November of 2020. The investigators looked at dried blood spots that had been collected to perform testing for antibody to the SARS-CoV-2 nucleocapsid protein and the spike protein, the two major viral antigens. The nucleocapsid protein is expressed by the virus, but isn't part of the vaccines that have been used in South Africa, which contain only the viral spike protein. Thus, measuring antibody to nucleocapsid is a good proxy for previous infection, even in those who received vaccine, at least in the parts of the world that aren't using whole inactivated viral vaccines. The investigators looked at samples from about 7,000 participants from about 3,000 different households. Most were obtained prior to the date of the first identified Omicron infection. Overall, almost 70% had antibody to the spike protein, while about 40% had antibody to the nucleocapsid. Since only about a third of the population had received vaccine, this finding suggests that the measurement of anti-nucleocapsid antibody is not terribly sensitive as a measure of infection. However, there were indications that using both measures together was indicative of previous infection, as those with known infection or who had received a vaccine were more likely to be seropositive. Thus, in this part of South Africa, immunity levels were very high, even though vaccination rates were low, suggesting that there had been a considerable amount of infection during earlier outbreaks.
So, Eric, I think these observations highlight at least three important points. As we previously discussed with Dr. Feinberg on a prior podcast, the importance of public health infrastructure to be able to do proper surveillance to understand the transmission of SARS-CoV-2 and when it surges, as well as other viruses and other pathogens. And I think these investigators demonstrate the value of proper surveillance methodology to understand what's really going on in terms of transmission. A second important point, as you highlight, is understanding prior infection. And our thinking has been nucleocapsid is a way to understand who is previously infected, as we do with the hepatitis B core antibody serology. However, these data show us that that probably is not as reliable as we wanted it to be. Thus, the amount of prior transmission in a community based upon nucleocapsid antibody alone may not be as informative as we want it to be. And third, as we look at severity of disease and activity of treatments, be it vaccines or otherwise, we have to understand this in the context of background immunity, because that is different than in a truly seronaive population.
Lindsey, as to your second point about the reliability of anti-nucleocapsid antibodies in predicting who had been infected, this is a particular problem in parts of the world where there are high levels of vaccination. In South Africa, where there wasn't much vaccination, it's relatively easy to identify people who have anti-spike antibodies, and most of those have been infected since very few have received vaccine. But in a place like the US, for example, where there are high levels of vaccination, if nucleocapsid assays are not reliable for identifying previous infection, we really don't have markers. So it's very hard to identify those who've been previously infected simply by serology.
And what about the second part of the South African study, the trends in infection?
Well, first, it's worth saying that South Africa has had much more distinct outbreaks than many other countries. There have been 4 clear waves with a very low number of cases between waves. Because of this, we can compare the shape of the epidemic curve during the Omicron wave with that of other outbreaks. During Omicron, there was a relatively sharp increase in cases and a rapid fall after the peak, though this report, which only extends to mid-January, doesn't capture the entirety of the wave. The total number of cases was high, but not nearly as high as during the third wave, an epidemic largely caused by the Delta variant. This is different from places like the US, where the number of cases during the Omicron surge has eclipsed those of other waves. It's impossible to know why this is, but it might be related to the amount of immunity or the availability of and threshold for performing testing. But what's most striking about these data is the severity of disease. The rate of hospitalization and death is far lower during the Omicron outbreak than in previous waves of infection. These data support the general observation made elsewhere that disease is less severe with Omicron. Of course, it's very difficult to compare from country to country. The threshold for hospitalization has changed over time, and once again, the rate of background immunity in the population is far higher in South Africa than in many other countries. Nevertheless, it's clear that deaths during this time in Gauteng are much lower than we'd been seeing.
Eric, I think the understanding severity of disease with this viral variant is very challenging, as you suggest. First, we need to understand the infection force in the community and the testing strategy of that community. If someone is admitted to the hospital, are they admitted because of COVID or are they admitted with COVID? And that gets very challenging when, at least in some countries like the US and many European countries, routine surveillance testing is going on for hospital infection control reasons. Thus, we need to better understand surveillance testing that allows silent infection to be detected, therefore inflating the denominator of infected versus those who are more severely ill. This is a good thing, but it complicates our ability to understand disease severity. The other, which Steve, you raised, is how do we understand which mutations lead to increased virulence or decreased virulence? And these data suggest that there is less severe illness associated with Omicron. But is this due to certain viral mutations being less pathogenic? Or is this due to the population immunity to SARS-CoV-2 being so much higher? Therefore, different aspects of the immune system may be playing a role in controlling and limiting disease severity. Difficult to sort out in a single study where both forces are at work at the same time.
So there are, as you say, some reasons why there might be decreased severity of infection in the South African population. But what about the virus? Are there characteristics of this variant that might be associated with less severe disease?
I think the answer is maybe. It's very difficult to measure virulence of a virus. Much of what we know about many infections comes from animal models. But for SARS-CoV-2, the animal models are somewhat limited. Most of the animals we use just don't get sick, and they clear the virus relatively rapidly. So we're left with in vitro models, cell infection, which really don't recapitulate the whole chain of infection, the difference between different tissues getting infected and the interplay between the host inflammatory system and the virus. In other words, it's just tough to tell. There have been differences identified in the ability of the viral spike protein to bind to its receptor and the affinity with which it binds. And there have been other studies that have identified changes in uptake of virus, but it's really difficult to extrapolate from these to disease severity. So the answer, I think, is maybe.
So, Steve, I think we have been blessed with our sequencing capacity and our advances in structural virology. However, I don't think we know enough yet to know which changes in structure have downstream consequences in disease severity. So to some degree, the clinical data will inform which mutations may be associated with attenuation. So it's a bit of a circular bench to bedside, back to bench, back to bedside that needs to go on here. And as Eric raised, different variants actually have different pathogenicity in different animal models. So it's not as if one model can be established, but there is a variance in model by variant. And lastly, in particular, disease pathogenicity not only is directly from the virus, but is the aberrant host inflammatory response, which is uniquely species specific. And it is very difficult to recapitulate the dysregulation of the host inflammatory response, the human host, that is, in an animal model, given its intrinsic complexity.
So all of that being said, is there a trend here? Is there reason to think that the next variant will also produce less severe disease, or is that wishful thinking?
Well, it may not be entirely wishful thinking because although it's difficult to predict a direction of evolution, we do have continuing increasing immunity in the population, whether that's due to vaccination or due to infection. And at some point, we benefit from that. Of course, there is variation among variants. Some variants are going to be better or worse at infecting those with pre-existing immunity. But nevertheless, immunity is probably a good thing. And I suspect that we may have less severe disease. Now, having said that, of course, a variant could come along with a huge change. Lindsey before had mentioned how there's reassortment of genes that can occur in animal species that can result in gigantic shifts in which receptor the virus uses, for example, or important big chunks of the spike protein that could result in what's essentially a new virus. That's where this virus comes from, after all, is it developed in nature from a collection of other viruses that were assembled into SARS-CoV-2. But I do think there's reason for some optimism in that it's likely that overall disease will become less severe over time.
Absolutely, Eric. It's so hard to predict the future, which is why we shouldn't. However, the goal of evolution is for us to coexist. So from an evolutionary standpoint, the virus is better off if it causes less severe illness. And in fact, I'll come back to there are 4 other seasonal coronaviruses that we've all gotten and not really cared about. I'm cautiously optimistic that at some point, this virus will also evolve in a way that is analogous to the seasonal coronaviruses. There's a bit of hope there, but from an evolutionary standpoint, that is the virus's goal. The virus has little interest in making us sick. It wants to reproduce, and the less illness it causes, the better it will reproduce. And hopefully we'll get there. It's just a matter of how long does it take.
So coming back from the future to the present, today in the United States and in most of the world, the Omicron surge is declining, and we appear to be entering another time when transmission is low. So what lessons can we take away both from Omicron and from the pattern of outbreaks that we've seen?
That's a very difficult question, I think. We have really, in a place like South Africa, where there were clear 4 waves, we have 4 experiments, and they all can suggest different conclusions. Getting back to your previous question, yes, severity has decreased, and that may be some combination of pre-existing immunity and some viral characteristics. But we don't know that the next variant will be less virulent. In fact, although both Lindsey and I just said that we think the grand direction of disease is toward less virulence, any given variant could violate that rule. And so without even more experience, it's hard to know. But the idea of SARS-CoV-2 as an endemic disease, as opposed to a pandemic disease, I think is probably quite reasonable at this point. It does seem that we have tools for this virus, both to prevent it and to use therapeutically. And as long as we can utilize those in the best way and continue to produce new tools, perhaps new generations of vaccines and new generations of drugs to treat people once infected or even prevent disease with drugs, I do think we're getting to a point where it's going to be something we live with and hopefully something controllable rather than a cataclysm as it was when it started.
So, Eric, I want to pick up on a couple of key concepts that you raised. I would argue it's endemic already, and we are living with it. The question of epidemic episodes that are associated with augmented severe illness, which then gets to the question of what is the outcome of interest. And I'm not sure we can get the genie back in the bottle and have SARS-CoV-2 eradicated from the planet. I think we will live with it. The question is, do we live with it as a common cold, or do we live with it as a severe pandemic causing severe illness? And I think that in part what the data from the study we're publishing this week show us is that broad swaths of the population have been infected. We have increasing vaccination across the population. So we now have growing mixed immunity. I think as we move forward, we're going to have proper surveillance to know if a more virulent version arises, which may not happen, and virulent in the context of significant community immunity. And then how do we protect our vulnerable members of our population? So our strategy may change from population-wide intervention to strategic framing of who's at highest risk for complication. How do we protect them with testing, with prevention strategies, and with early treatment? For example, our cancer patients, our patients on immunosuppression, our patients with severely weakened immune systems, our seniors who live in congregate environments. So, Steve, I think we have to evolve our thinking from no COVID to how do we live with it as a common cold for most of us and protect those at highest risk. Because I think we now are going to have mixed immunity of natural infection and vaccine-induced immunity in most members of the community. And therefore, it's a different problem when another infection occurs versus a true primary infection.
Eric and Lindsey, we've been talking today about global health, which is what we talk about every week. And today I wanted to acknowledge the loss of a giant in the field of global health, your colleague and a frequent contributor to the journal, Paul Farmer.
Steve, I've been reading the obituaries and everything they say is true. I think that we have a slightly different perspective on Paul as a colleague and a friend because we knew him as a person. And one of Paul's distinctive characteristics, which totally fits in with him as a global health icon, was his kindness. Paul was fun to be with. He had a good sense of humor. He was self-deprecating. He was humble, and he was incredibly friendly. He made friends with everyone he met. If you walked around the hospital, if someone saw your badge that said you were from infectious disease, whether they were cleaning the floor or changing sheets in a room, they'd say, "Oh, do you know my friend Paul Farmer?" In fact, I have to credit Paul with getting me out of some jams in the past. Once I went into the garage and my card didn't work. And the garage was very strict. And an attendant came over and said, "What's going on?" And I said, I can't get in. He said, "Well, if it's not coded, you can't park here." And he said, "Well, where are you from?" And I said, I'm from infectious disease." He said, "Oh, do you know my friend Paul Farmer?" And he let me in. So thank you, Paul, for getting me parking. But thank you for everything you've done for us as individuals and for the world.
So, Steve and Eric, these are sad times. Remembering Paul and the 30 years that we've worked together, leads me to reflect on our many interactions and how much I've learned from him. Over the years, discussing so many things from patient care to global health, J.R. Tolkien and the Lord of the Rings and incredible stories, and how his brother was a professional wrestler. And I remember Paul saying to me how trapped in his scrawny body is a big wrestler like his brother. And that just makes me think about how Paul really was just such a big wrestler, able to wrestle the biggest problems that we face globally, the biggest health issues, and to not settle for the convenience solution, but to go big and make it better. And to inspire each of us to go big and make it better and not settle. And for that, I'll just be forever grateful to Paul for that inspiration to really tackle the biggest health problems in the world and to make it better. I think we'll all really miss Paul.
Thank you, Lindsey. And thank you, Eric.